A very good evening to each and every one of you. I'm Hefei, the director of STIAS, and it's a pleasure to welcome you to this evening's public STIAS lecture. If you followed the news headlines in 2017, the name Mitzius should perhaps ring a bell. If not, then let me inform you that that is the name of the Chinese satellite which was launched in 2016 and served to transmit on the 27th of September 2017 a shared quantum cryptography key between Beijing and Vienna, a distance of about 7,400 kilometers, and allowed the presidents of the Chinese and Austrian Academies of Sciences to communicate via an absolute secure video link. So this evening we have the privilege of welcoming the leader of the team behind that technological breakthrough, Professor Jian-Wei, as the speaker at this public STIAS lecture. He's the director of the Division of Quantum Physics and Quantum Information at the University of Science and Technology of China in Hefei. And I've noted that descriptions of his work are often phrased as breakthrough, first, and world record. The world certainly took note of the September 2017 communication between Beijing and Vienna. In that same year, that's last year, Jian-Wei was named on Nature's 10 list. That's the leading science journal, Nature's annual list of 10 people who mattered in science in a given year. And in December last year, he was also named on the Time magazine's list of 100 most influential people of 2018. So the Chinese-Austrian link I referred to is no coincidence. Jian-Wei holds a PhD from the University of Vienna, and during his early career in Austria and as a PhD student, and later also as a senior scientist, he and his colleagues achieved a seminal series of breakthroughs in quantum communication. Already then, his first quantum teleportation experiment, which was reported in 1997, was selected by Nature as one of the 21 classic papers in physics published by Nature in the 20th century. Jian-Wei work has ranged from the conceptual and theoretical to a current strong focus on experimental and technological work. He's authored more than 190 research papers, including 14 in the esteemed journals Nature and Science, and 24 in specialized journals such as Nature Physics, Nature Photonics, and Nature Nanotechnology. His work in the field of quantum information and quantum communication has been selected by, for example, Nature again as a celebration of physics in 1999, as a feature of the year in 2012, and as one of the science events that shaped the year in 2016. Similarly, Science named him as one of those who carried out a breakthrough of the year in 1998, and the American Physical Society, no fewer than 5 times, have already noted or listed him as among those who achieved the top physics stories of the year. Similarly, the Institute of Physics of the United Kingdom included him 6 times in their lists of breakthrough of the year or highest or highlights of the year. Jian-Wei is the chief scientist for the Chinese Quantum Science Satellite Project and also of the Beijing to Shanghai 2,000-kilometer Quantum Communication Backbone Project, which is the world's first long-distance quantum-secured communication route and was put in service in August of last year. This, by the way, links these 2 cities with a highly reliable and expandable secure communication expressway. I read that Jian-Wei next big plan is, quote, a $2 billion 5-year initiative which is focused on quantum communication, metrology, and computation, which is positioned to mirror a $1.2 billion European flagship initiative on these topics, and which was announced in 2016. So, Jian-Wei, we wish you success with this venture, but from now we look forward to hear how you will be linking Einstein's curiosity to current quantum technology. So, please do. Thank you. So, you just turn the lights.
Yeah. Okay.
Yeah.
So, many thanks for your kind introduction. Ladies and gentlemen, good evening. So it's a great pleasure for me to be here. First of all, I would like to thank the organizer for the invitation, which gives me a chance to share with you my view. And actually, I have never been in South Africa. So I accept the invitation immediately after I received an email from Professor Arthur Eckhart. So thank you, Arthur, for the invitation. So the title of my talk today is Breaking the Wall to Quantum Engineering. So in this talk, I'm going to show you how Einstein's curiosity leads to new quantum technology. So we are from the CAST Center for Excellence in Quantum Information and Quantum Physics. So I am the director of one of division, so the Quantum Information and Quantum Optics division. So the main research field of our division is twofold. So the first one is the test of quantum foundation with the technology in quantum optics. So the second one is we also do research in quantum information processing. And for example, in the research of quantum communication, we are currently working on a fiber-based quantum communication network and quantum repeater with hard-coded atom quantum memory and free space quantum communication to establish a global scale quantum communication network. And also, we are working on quantum computing and quantum simulation. So in order to achieve scalable quantum computation, we are currently focused on multi-photon entanglement and also superconducting qubit and hard-coded atom. In the meanwhile, we also explored all the technology developed in quantum communication and quantum computation for various applications in high precision measurement. So, paleobiology tells us about 100,000 years ago, Neanderthalian and Homo sapien had coexisted in Europe for some time. Neanderthalian was stronger than Homo sapien and even had a larger brain than modern human. But why did Homo sapien finally win the evolution battle and become our ancestor? So one of the reasons is because Homo sapien and create proto-symbol and language by which they can communicate more effectively and form cooperative and society. So therefore, information exchange is the key factor in human evolution. So in information exchange, privacy protection is the key factor. And only with privacy protection can people have the freedom to think, write, read, and speak, and so on. So, and it's fair to say, human civilization cannot exist and develop and without privacy protection. So in return, the social progress makes information exchange more efficient. So therefore, the information exchange has been and will continue to be accomplished by the human evolution and the social development. So there are two everlasting questions. There are two everlasting questions that we always seek to answer. So how to make information exchange more efficient, how to protect privacy effectively. So in information science, so the answer is computing power and information security. So achieving secure information transfer has been the dream of humans since ancient times. And for example, Spartan in 700 BC, they already used the cipher tool named STIAS to ensure secure information transfer. Since the message is written upon a wound strip, and it will appear as illegible jumble of letter to anyone who does not bear a side tail with the appropriate diameter. And around 50 BC, and Julius Caesar from the Roman Empire and ancient Roman Empire, he also invented a shift cipher to ensure secure information transfer. However, all these ancient encryption systems can be cracked. And for example, and the cipher shift can be cracked by analyzing the frequency of the occurrence of a letter, as shown in here. And because, and we know, for example, in English, so the frequency for the occurrence of each letter is fixed. So, and although you use the shift cipher, but by analyzing and the frequency of occurrence, you can still figure out which letter is A, which letter is B, and so on. So historically, we know every advance in classical cryptography has been defeated by advance in cracking. So during the Second World War, Alan Turing successfully cracked the German Enigma machine, and in modern cryptography and the widely used public key encryption system, RSA 512 was cracked in 1999, and 706A was cracked in 2009, and now even RSA 1024 has been considered unsafe. And therefore, from experience, and we could have some sort of conclusion, and all the classic encryption methods that depend on computational complexity can be cracked in principle. Therefore, it has been long suspected, as pointed out by novelist Edgar Allan Poe, and human ingenuity cannot concoct a cipher which human ingenuity cannot resolve. So we always, in some sort of an endless battle. So on the other hand, the computing power owned by human is very limited. At present, the world total computing power is insufficient to search a target into to the power of 8 databases within a year. So one of the major technological limits is that the Moore's law that predicts the transistor density doubles every 18 months has come to end. This is because the size of the transistor will soon reach atomic scale, so that the electron tunnel effect will appear, and thus the circular value, the circular state of 0 and 1 in the transistor cannot be well defined anymore. So, fortunately, quantum physics, after 1 century of development, came to the possible solution for the problems I just mentioned. So, for the computing power and for the security stuff. So now, I would like to first give a brief introduction about the quantum superposition principle. As we all know, for a cat in the classical world can only be either in alive or dead state. However, according to quantum superposition principle, a cat in the quantum world can even be in the coherent superposition of alive and dead state. So physically, any 2-level quantum system can be used as a realization of qubit. For example, we can explore the 2 polarization states of single photon, horizontal and vertical, to encode 1 bit of information. Then, according to quantum superposition principle, the polarization state of single photon can even be in the arbitrary superposition alpha h plus beta v, where the 2 complex numbers satisfy the normalization condition. Suppose now we want to know some information about the 2 coefficients alpha and beta. One simple way is to perform a measurement onto the single photon by sending it through a polarizing beam splitter, which reflects horizontal and vertical component and transmit the horizontal component. Then in the specific experimental run, with the probability alpha squared, the photon will found to be in horizontal polarization state. And with the probability beta square, the photon will found to be vertically polarized. So in such a simple analysis, and we know no measurement is sufficient to reveal all the information which is necessary to reconstruct this unknown state. This consequently leads to the quantum non-coherent theory, which states an unknown quantum state cannot be copied precisely. As we will see later, this is actually the foundation of security of quantum cryptography. So when we apply the quantum superposition principle to multi-party system, we are used to conception of quantum entanglement. And suppose we have two cat in the quantum world, then they can be even in the coherent superposition of alive, and dead state. Then if we perform a measurement onto one of the two cat and it's found to be in alive state, then the second cat will instantaneously and collapse into the corresponding alive state, no matter how far away they are separated. So Einstein, for such a phenomenon as a spook action at a distance, so for a quantum system consisting of two photons, 1 and 2, they can be in one of the following four Bell states, the so-called maximally entangled state. So the reason why Einstein called quantum entanglement as spook action at distance is because, and he believed, the outcome of a measurement of any physics system is determined prior to and independent of the measurement. And furthermore, the outcome cannot depend on any action in space-like separate region. So this an opinion is very much and is seemingly quite a reasonable assumption of local reason. However, quantum mechanics tell us initially the individual state of the two entangled particles are not identified. The measurement outcome on particle A will not only determine A state, but also the state of particle B immediately. So therefore, in 1935, Einstein, Polsky, and Rosen, they published a famous paper questioning the completeness of quantum mechanics due to its theory supporting spook action at distance. However, at that time, both local reason and quantum mechanics can explain the perfect correlation. Okay, so we do not know how to experimentally test which opinion is correct. So such argument remain at the philosophical and level for almost 30 years. So in 1964, John Bell proposed an equality, the so-called Bell equality, by constructing an observable from the measurement result of two entangled particles. Then, according to Einstein local reason, the maximum value of this observable is 2. However, according to quantum mechanics, the maximum value of this quantity can reach 2 square root of 2. Therefore, in principle, we can perform experimental test. So actually, much earlier than Bell's theory, based on a proposal by Jian-Wei and a famous Chinese woman scientist, Wu Jianxiong, and he created the first quantum entanglement in laboratory at that time at Columbia University, and by observing quantum angular quantum correlation of scattering annihilation radiation. So after the Bell inequality, a number of experiments has been performed by various groups to test the Bell inequality. All the experiments confirm the correctness of quantum mechanics, while still with some loopholes that need to be addressed further. So one of the remaining loopholes is the so-called freedom of choice loophole. That is the random number generated that determine the choice of measurement basis for a Bell test could be prior correlated, because the random number generated already exists for a long time. So therefore, the choice of the measurement basis are not or may not be truly random. So we have this loophole. The second remaining loophole is the so-called collapse locale loophole or Schrödinger cat loophole. So according to Schrödinger-genetic element, so the measurement outcome, for example, the Kerr state in the closed black box may not be well defined until it is registered by human consciousness. So this implies all the realized events may have never been space-like separated, as pointed out by several people. So how to solve such a problem? So one of the possible solutions to the freedom of choice loophole is to use random number generated with cosmic photon. This is because the states of photon from to remote and select objects are independent if we believe nature is not so malicious that premeditating from billions years ago to jeopardize the experiment. So I mean, they cannot really already know we will perform this experiment after a million years, right? So, and that's one thing. Then the second possible solution to close both loopholes, the so-called freedom of choice loophole and the correct locality loophole, is to perform a Bell test experiment with a human observer. So why we need a human observer? This is because the artificial machine does not have free consciousness. For example, as shown in the famous television, so in the West world, and although the AI robot thinks she has free consciousness, but actually every her future action has been well predetermined in advance by the remote control station. So therefore, as proposed by Lange and his cohort, with human observer, then the basis choice for the Bell test and measurement can be made by humans' free consciousness. And also, the measurement outcome can be defined by humans' consciousness. However, this will require the quantum signal transit time exceed human reaction time, and which is typically 100 milliseconds, which will require the intended distribution at a distance on the order of 1 light second, which is about 300,000 kilometers away. So, for example, is on the order of the distance between the Earth and the Moon. However, although the test of quantum non-locality has not yet reached a final end, so the physicists have developed groundbreaking technology for coherent manipulation of quantum systems. These consequently lead to emerging quantum information science, and such as quantum communication, quantum computation, and so on. While with quantum communication, one can ensure unconditional secure information transfer, and the quantum computing can greatly enhance the computing power. So, quantum key distribution is one of the best known quantum communication protocols. For example, we can explore the so-called BIP84 scheme to perform a single photon-based quantum key distribution. In the BIP84 protocol, artists could first send a sequence of single photons which are randomly polarized along horizontal vertical basis and 45 and minus 45 degree polarization basis. Then, the Bob could perform a polarization measurement onto the received photon by randomly choose horizontal, vertical, and 45 degree polarization basis. By keeping those results where they have chosen the same basis, one can generate a shared secret key, and then with the help of one-time pad encryption method, we can ensure unconditional secure information transfer. The existence of evil job can be easily found out by broadcasting a subsequence of the shared key and compare the quantum bit error rate. And similarly, following the idea by Otto in 1991, one can also explore the perfect polarization correlation to perform intelligent-based quantum key distribution. I will come back to this point and later. So another interesting application of quantum communication is quantum teleportation. To have a better understanding of quantum teleportation, let us consider the following example. Suppose I brought a gift inside a suitcase from Shanghai to Stellenbosch, but unfortunately I forgot to bring the key. So what can I do? I can simply phone my colleague in Shanghai, then he can perform measurement onto the key and send me the scan information. Then I can go to the key shop here to duplicate a key by which we can open the suitcase. But what will happen if the quantum key in a low superposition of alpha h plus beta v? As I just mentioned, according to quantum non-closing theory, no measurement is sufficient to reveal all the information which is necessary to reconstruct this quantum key. Then what we can do? It seems a simple way is to directly send the quantum key from Shanghai to Stellenbosch. But we know the quantum state is very fragile, can be easily destroyed by noise in the quantum channel. So fortunately, and following the idea by Burnett and his co-work in 1993, one explored quantum teleportation to transfer an unknown quantum state from one particle to another remote particle without sending the particle itself. So how to do that? So to do so, Alice and Bob first share a maximum intent state, say in 5+ state. Then the overall state of particle 1, 2, 3, and it can be written in terms of the 4-barrel state of particle 1 and 2 in the following form. And now, and let Alice perform a barrel state measurement between particle and 1. Then with the equal probability 1/4, we can project the photon state, project the state of photon 1 and 2 into one of the following 4 barrel states. Then the remaining particle, so the state of the remaining particle 3 will be cracked into one of the following corresponding states. Then the state of particle 3 can be further converted into the original state of particle 1 by applying unitary transformation conditioned upon the barrel state measurement result. Here, I would like to emphasize the final state of particle 3 is not a copy of the initial state of particle 1, because during the teleportation process we perform and no measurement is performed of particle 1 to reveal its position information. So after the barrel state measurement between particle 1 and 2, the state of particle 1 already in a maximally mixed state contains no information of alpha and beta. This is exactly the reason why quantum teleportation protocol can escape the restriction of quantum non-coherent theory. So teleportation is not a copy, it's rather a result of quantum teleportation. So quantum teleportation is very much like the way to achieve Star Trek in science fiction. Although it's far away and from teleporting a person, but one can easily teleport a quantum state with a network. So this is actually an essential ingredient for distributed quantum information processing, and actually is also essential ingredient for quantum computation. So interestingly, and the state of one particle of intact pair can also be teleported. And for example, and we start from 2 intact pair 1, 4, 2, and 3. If we perform barrel state measurement on particle 1 and 2, then we can enhance particle 3 and 4, which and never interacted in the past, following the idea by Markovsky and Arthur and so on. So this is a very an interesting protocol and play an essential role in long-distance quantum communication, as I will show you later. So, and with the help of quantum parallelism, one can design various quantum algorithms to solve classically hard problems. And the quantum computer encode information and use qubit to encode information which can be, as I just mentioned, in coherent superposition states. So therefore, the information represented by them can be processed in parallel. Therefore, for example, we can evaluate, we can use quantum parallelism to evaluate a function fx for many different values of x simultaneously. This can thus lead to exponentially speed up in principle. So one of the most famous algorithms, a quantum algorithm, is a Shor algorithm, by which we can efficiently factorize the large number and thus break down the public key encryption system if we can really construct such a computer. And for example, in order to factorize a 300-digit number, and with the classical T-Hertz computer, it will take us 150,000 years. However, it will only take the T-Hertz quantum computer 1 second. And also, the superpower of quantum computer can also speed up, significant speed up, weather forecast, financial analysis, drug design, and so on and so on. So in the following, and due to the time limitation, I will only discuss the recent progress in the field of quantum communication. So the first proof of concept demonstration in quantum key distribution and quantum teleportation was performed in 1992 and 1997. However, in this experiment, the achieved distance is very short. It's only about 30 centimeters. So distance is very much limited. On the other hand, and it was found there are serious security loophole of QKD in all the former QKD experiment due to the imperfection of realistic quantum device. The first security loophole was caused by imperfect single photon source. Since there are occasionally two identical photon events, and from the pulses of the caused single photon source, then the so-called photon number split attack and will allow an even job to selectively suppress single photon signal while splitting the two photon signal by keeping one copy for herself without being noticed by others in the board. So therefore, due to the imperfection of single photon source, the secure distance of QKD in this case is only on the order of 10 kilometers. So the application is very much unlimited, because if it's only 10 kilometers, so we can drive a car and talk to my friend, then probably we don't need to use quantum key distribution. So therefore, we have two major challenges toward large-scale secure quantum communication before we can promote any practical application. So the first one, we have to extend distance. So the second one is we have to solve the problem of the security loophole caused by imperfection of realistic quantum device before we can promote any practical application. And for example, due to the exponential photon loss and the coherence in the quantum channel, and also due to the probabilistic photon source, it's extremely difficult to extend the distance for quantum communication. And for example, in order to achieve 1,000 kilometer fiber quantum communication, even with a perfect 10 gigahertz single photon source and ideal single photon detector, only 0.3 photon can be transmitted on average per century. So it's really of no use, if we cannot solve such a problem. So one of the possible solutions is to use quantum repeater. So the central idea of quantum repeater is to solve the photon loss problem via entangled swapping, and solve the coherence problem via entangled purification. And this would impose three major requirements: entangled and to experiment. So we have to rely entangled swapping with high precision, entangled purification with high precision, and quantum memory with high performance. So for example, and this nice idea, also there's some contribution, there's some, an important contribution from Arthur. He is also in the audience. So the first experiment for entanglement and swapping was performed in 1998, and after a few years, in 2003, we managed to report the first fault-tolerant entanglement swapping by using a high-precision 4-photon interferometer. And also in 2001, and we proposed a practical scheme for visible intent purification with linear optics. And in later 2003, we performed the first high-precision entanglement purification. So why we need the quantum repeater? So the reason why we want to have quantum repeat is for the following. And because the intent photon source is always a probabilistic source, and in each run, the probability of emitting one EPR pair or one intent pair is P. Then, if without quantum memory, then the only thing we need to do is we perform the intent swapping. And because each pair is a probabilistic one, then the total cost of a result in multi-stage realization is proportional to 1/p to the power of 2n. So such a scheme is not scalable. Because, for example, for each state, p is equal to 0.1. If we have 10 amines and sublocation, then this will be proportional to 10 to the power of 20. So such a scheme is very inefficient. However, if we have a quantum memory and we know where this pair is created, and also we can store them on demand, then after all the EPR pair are ready, then we perform intent purification and intent swapping. The total cost of result is proportional to 1/p squared. And is about 100. So in this way, we can achieve efficient distribution of quantum entanglement between distant locations and achieve scalable quantum network. However, in the time around 2003, quantum memory was still a botanic. So we don't know, how to find a proper system to achieve quantum memory. So while continue to develop quantum repeater, we also pay more attention to solve the security loophole due to and with the realistic device. So in 2005, and it was proposed, with the help of decoy state QKD scheme, one can solve the problem caused by imperfect single photon source. So in the decoy state QKD protocol, an artist could and switch the power of a laser up and down. Then, the bulb can easily obtain the received probability of single photon and the quantum bit error rate for both intensity for both decoy and signal state. In this way, the existence of Eve can be easily and verified if he tried to perform any an eavesdropping. So in 2007, two and the independent group performed decoy state QKD experiment over 100 kilometer fiber, and soon after that, after 2 years, and also the distance is extended to 200 kilometers. Okay, then people are quite happy. So the single photon source problem can be solved. But unfortunately, around 2010, and a new security loophole was formed due to the imperfect single photon detector. So while we solve the problem and for the sender, then we find a new problem for the receiver. So in this case, one can send a specially tailored strong line to blind the single photon detector, so that the single photon detector can only respond when the light intensity is greater than threshold I. Then in this case, if Eve send a light beam with intensity 1.6 as shown in this figure, then only for the case if both polarization bases are the same as the incident light, then the detector will have a click. So in this way, as the eavesdropper can fully control our detector. So the detector can only see those events and where the eavesdropper hope you to see. So one ideal solution for such a problem is to use the so-called measurement device independent QKD, by which one can immune to any attack on detection. So as soon as, for example, if we have measurement device independent QKD, so the measurement machine even is made by North Korea, so these two people can still communicate and at ease. So to do so, we need to develop high precision interference technology between two independent lasers. They are separated far, far away. And for example, in our experiment, we managed to develop high precision synchronization system between two remote independent lasers so that the relative time jet of 100 kilometer fiber can be controlled to be less than 10 picosecond. So in 2013, we did the first experimental demonstration of MDI QKD over 50 kilometer fiber. Then in 2016, and with the help of improving our protocol and also increasing the repetition rate and also using a high efficiency single photon detector, the secure distance is extended to 400 kilometers. With these two secure loop hole closing, information selectively secure QKD with trustful release device can be finally achieved. However, we still need to develop quantum memory to extend distance. As I just mentioned, due to the limitation of quantum non-coherent theory, so the quantum signal cannot be amplified because you cannot make clone and you cannot make copy. So therefore, so the longest distance of MDI QKD fiber is about 400 kilometers. So for teleportation in free space, is about 100 kilometers. So it's extremely difficult to beyond on the ground and this distance. So we still need to develop quantum memory to achieve a practical quantum repeater. Therefore, since 2003, and we start from an empty optical table for quantum memory with cold atom at the University of Heidelberg at that time. So after 5 years effort in 2008, and we managed to implement a robust quantum repeater with two laser-cooled atomic ensemble which are connected through a fiber, through a 300 meter fiber. So of course, simultaneously, there are also some other approach for other group, for example, Kimball's group, Kushmich, Lukin, and Harry, and so on. There are many other groups they are working on so other approach. However, in these experiments, the performance is very poor. In order to really achieve long-distance quantum repeater, we have to ensure both long lifetime and high retrieval efficiency. On one hand, the storage time must be long enough to ensure an every node to create an entangled path. On the other hand, the storage quantum state must convert into photon with sufficient high efficiency to establish remote entanglement. However, in our 2008 experiment, the lifetime is only about 1 microsecond, while with a 35% retrieval efficiency. So from this figure you can see, in order to achieve a quantum repeater for 500 kilometer application, from here to there, and 8 order of magnitude need to be improved. So in 2012, we managed to improve and the lifetime by 3 order of magnitude, but still we have, and also with high and retrieval efficiency. In this case, from here you can see we still need to improve the lifetime by 2 order of magnitude. So in 2016, with the help of 3D optical lattice confinement and also some ring cavity, we managed to avoid all the decoherence effect caused by atomic thermal motion and collision and so on. Then we managed to enhance the lifetime from 3 milliseconds to 200 milliseconds. So which is in principle good enough to support quantum repeater enabling quantum communication at a range of 500 kilometers. However, to achieve a practical quantum repeater, we will still need at least 10 more years or probably 20 more years. Therefore, since 2002, as early as back in 2002, we also considered another possibility to achieve global quantum key distribution. That is, use satellite in free space. This is because as and this is because the effective thickness of atmosphere is only about 10 kilometers. So and the propagation path. So the propagation. Okay. So the path of single photon propagation, and most of the propagation is in outer space with negligible absorption and decoherence and turbulence. So in this way, we might able to achieve long distance quantum communication. So we spent the past decades to perform various ground tests for satellite-based quantum communication. So in 2004, we did the first experiment for in-time distribution over a distance of 30 kilometers. In this experiment, we for the first time well beyond the effective thickness of the allosphere. And moreover, after a couple of years' effort, in 2011, we managed to implement quantum in-time distribution and quantum teleportation over 100 kilometer free space channel. And in this experiment, we verify the visibility to achieve quantum communication and via high loss satellite to and ground channel. For example, and you can see, I mean, in our experiment, the tolerable channel and loss can up to 50 dB, but for the calculation, so the loss for uplink of ground to satellite is on order 45 dB, and moreover, so the last tolerable channel loss in this experiment is 85 dB, but for two downlink between satellite and two ground station is about 75 dB. So we can see our technology is sufficient to tolerable high loss satellite to ground channel. So finally, in 2012, we report a full-scale verification toward satellite to ground quantum key distribution under simulated condition of satellite motion and vibration and turbulence and high channel loss, overcoming all the demanding conditions for the ground to satellite, for the satellite to ground quantum key and distribution. So through this ground test experiment, we have mastered the key technology for quantum communication with low orbital satellite, such as the high precision and acquiring point and tracking system, and also near diffraction limited far field divergence angle, and also high precision synchronization. And also we achieve ultra high energy resolution, by which one can even detect from Earth a single mesh fire lightning on the moon. So with all this technology, after 12 years effort, in 2016 August, the first quantum science satellite missile was successfully launched. So the satellite has a weight of 640 kilograms, and with some synchronous and orbital with altitude 500 kilometers. So the missile satellite has three missions. So the first one is to use the satellite as a trustful relay to achieve quantum key distribution between satellite and ground, and also between two ground stations. So in the first experiment, we managed to achieve 1,000 bits per second. And this is the key bit rate very recently by optimizing the performance of our satellite and the ground station. So the key bit rate has been increased to 400,000 bits per second. This is good enough for some preliminary and application in data transfer and so on, which actually is 20 orders of magnitude higher than using telecom fiber channel at 1200 kilometers. And moreover, our second mission is to achieve in-time distribution between two ground stations which are separated by distance 1,207 kilometers. So in this experiment, we managed to perform the first space scale test of spook action at a distance under strict Einstein locality condition. And moreover, and we also perform experiments for quantum teleportation from between ground station and satellite, and with the distance with a maximum distance of 1400 kilometers. So very recently, using satellite as a trusted relay, and in collaboration with our colleague in Austria, and we also achieved intercontinental quantum key distribution between Vienna and Beijing with a distance of 7,600 kilometers. Currently, collaboration with Italy, Germany, Russia, and Singapore are also going on. So we hope through international collaboration to test the visibility of global quantum communication. So, and one may ask, is it possible to perform quantum key distribution between ground station without using the satellite as a trusted relay? So the answer is yes. So very recently, following the scheme by Arthur Eckert in 1991, and we already performed experiments to achieve entanglement-based QKD over 1,120 kilometers. So in this experiment, so the violation to the bioequality is quite good, and the observed quantum bit error rate is about 4.6. Then the final key rate is about 0.4 bit per second, although it's still very low. But with our newest developed entangled photon source, because we already have a GHz entangled photon source, so in principle, in the future, it should be possible up to 10,000 bits per orbiter. And because in this case, and even the satellite is controlled by your enemy, once bioequality is violated, so the security of QKD can still be ensured. So, and according to Gilles Bassat, and he said if one can perform such experiment, this in some sense would achieve the holy grail that all cryptographers have been dreaming of for thousands of years. So, and moreover, and since greatly enhance the quantum communication efficiency. So one pre-requirement is to ensure the quantum satellite to work in solar radiation background. So in 2016, we performed another ground test experiment to achieve a long-distance free space QKD in daylight and verify the visibility of quantum and constellation. So in the next 4 years, we are going to launch 3 or 4 low orbital satellites to form a quantum constellation for real application. And also, and very interesting, and also interestingly, the satellite-based technology can also be used for investigation of fundamental physics at the interface of quantum physics and gravity. For example, currently we are working on an experiment to test gravitation-induced decorrelation of entanglement. So according to this theoretical proposal, if we have some gravitational-induced decoherence, then we will see such a curve, and if no decoherence, we will see such a curve. So currently, we are accumulating data to see whether this prediction is correct or not. And having achieved long-distance quantum communication and solving the locality and the security loophole, and we also, so finally, and the quantum communication has become a viable technology under realistic conditions. So in the recent years, we have been working on large-scale metropolitan and network. For example, in 2012, we have a large-size intracity common key distributed network with 46 nodes. For various applications such as bank transactions and so on. And also, in the end of 2016, we established a Beijing-Shanghai quantum backbone network. So with 4 local networks in Shanghai, Hefei, and Jian-Wei, and Beijing. Then and this intercity quantum communication backbone has 32 trusted relays. So the whole distance is 2,000 kilometers. And currently is for various applications, for example, financial application and public affairs and so on. So to finish my talk, I would like to mention our future and plan. So first of all, in the future, we hope to construct a global quantum communication infrastructure with satellite and fiber network. So in this way, a quantum internet can be established for global protect of data security. And also, with the help of the global quantum communication network, and we can, and combining photons from distributed telescope worldwide by quantum teleportation in space. In this way, in principle, we can gain an enormous spatial resolution. And for example, if we can do, if we can construct such a network, then in principle, we can even read on the Earth's license plate floating in Jupiter orbiter. And moreover, we can also use the same quantum communication network to construct a global, precise time information sharing network. With the help of an optic atomic clock and optic frequency transfer, we can gain 4 orders of magnitude better than the traditional microwave timing sharing on long time instability. So this technology is very useful for navigation like GPS and so on. And also, we are planning to launch a high orbital satellite to the geostationary orbiter. So in this case, beside QKD, and we also, the satellite will also carry on optic clock. And because in the outer space and the magnetic and the gravitation noise is negligible, so that we can greatly enhance the fractional instability of optic clock. So which will allow us to achieve a precision 10 to the minus 21. But on the ground, the better precision is on the order 10 to the minus 18. So if we can achieve this, and then use time inflation and effect, we can precisely detect gravitational redshift at different altitude of orbitals. Because for this satellite, we can change the orbital and gradually from low orbital to high orbital, then to a geostation. And also, suppose we have an optic clock in space with such a precision that one can even detect gravitational wave signal with lower frequency. So we can provide a new way for the detection of gravitational wave. And finally, as I just mentioned, we also want to do some experiment to close the remaining loophole. So very recently, in order to close the freedom of choice and the loophole, we also did an experiment and based on random number generation with cosmic photon. So the random number is generated by 2 stars. They are separated, with an 11 light years. So then, and we use this random number to perform a Bell test. In the meantime, also we and close both detection and locality loophole. So in the future, we are going to use quasar to perform the generation of random number. In this way, we can push the history back to 10 billion years ago. So the nice thing is, such a technology can be used immediately for the so-called device-independent quantum random number generation. In the recent experiment, we already generate unpredictable random number even with untrusted device. So in the future, we want to exploit and this way to form new standard of randomness. So also, in order to close both both collapse locality loophole and freedom of choice loophole, and we also want to in the future perform large-scale tests with human observer. So very recently, we already performed a ground test with human surprising random measurement over a simulated high loss between Earth and the Moon. So this is the loss is about 100 dB. In our experiment, about 103 dB. So which shows the possibility, and even with such a high loss, we can still and perform violation of Bell inequality. And moreover, and actually through the big Bell test collaboration and the 12 labs over the world, and run bell tests together with a random number generated by and the free will of 100,000 worldwide volunteers, and so on. So therefore, in the future, we are going to and join the China's future moon landing project. Then we can perform intent distribution between moon and Earth, and then we can complete the large-scale bell test with human observer. So thank you for your attention. Yeah. So this is
I still have to catch my breath. Thank you, Jian-Wei, for that remarkable overview of the history and development of quantum communication. I presume you will be happy to answer a few questions if anybody wishes to probe.
Okay.
Perhaps can you just identify yourself and then pose the question, please?
Hi, Davy van der Never. I'm from engineering here at Stellenbosch University, so this is completely out of my field. So, excuse me if I'm asking a stupid question, but maybe you did answer it, maybe not. But somewhere in your talk you mentioned the human observer effect. So, I want to get your opinion. So, I don't know if you answered it because a lot of this, about 47% was over my head. But do you believe that consciousness collapses the wave function or not? And maybe on that question, so there's these different interpretations of quantum mechanics. So does consciousness play a role? And then also your opinion on the many worlds interpretation or the standard Copenhagen interpretation? Mm-hmm. Thanks.
Okay. So actually, everybody can ask very important question, especially for quantum mechanics. No question is stupid, So I don't know the answer, for your question, but I also have the same question like you. So but the thing is, I think the only thing what we want to use human observer to perform bell test is because this is the last thing we can do. And also we know, as I just mentioned, for the traditional, artificial machine, we think they do not have free consciousness and whatsoever, because for them, like our computer, everything already, well known, so there's no uncertainty inside. But I'm not sure whether my point is correct. But I still believe it's interesting to do. So in this way, we can push the boundary, or we can push the limit of quantum mechanics. We can develop, very good technology for practical application. And because actually, even for the people from our field, we have also two different opinions. Some is, okay, we already believe quantum mechanics, so it makes no sense to perform tests of quantum non-locality. But some people think, okay, we should perform more and more tests of quantum foundation. But now, so the lesson tells us is because of the test of quantum foundation, which leads to the new quantum technology. So it's in some sense worth to do so. So, but I hope in future, if we have some new result in the study of quantum computation, maybe in some sense can be of some help to answer the consciousness or origin of consciousness. But I have no idea. I don't know. It's totally open question.
Delsing, and then you are Salzburg. Yes.
So I have a question on your atomic clocks and the great improvement you can get by going to optical clocks.
Right.
So will that also be reflected in the precision of our GPSs? So or are there other bottlenecks that will actually limit the precision of GPS?
Mm-hmm. I think for the current atomic clock on the ground, so the precision already well enough for GPS. It's already much beyond the need of GPS. But the thing is, if we further improve the precision of atomic clock, so we have ability to study, for example, as I just mentioned, So the, just a second, and to see the gravitational redshift at different attitude of an orbital. Actually, this has been seen. So the gravitational redshift has been seen in some experiments. But the most interesting thing is we can provide a new way for studying gravitational wave, signal at lower frequency. Yeah, because normally we need to build a very big interferometer to see the gravitational wave. But in this case, we only need 2 atomic clocks, then with the quantum communication channel for the timing sharing. So, and which will provide a new way for hearing the noise or the voice of the universe. Yeah.
Yes, my name is Joachim Safelsberg. I'm a fellow at STIAS. Much of what you said, or some of what you said, I did not fully comprehend. I'm a sociologist, so in a very different discipline. But I do know that everything you talked about happens in a social, political, and geopolitical context. And I was wondering, even if this is not your area of expertise, if you could say a little bit about the social, political, and geopolitical conditions under which these technologies can unfold and unfold their consequences.
Okay, so I think in the short run, if we really have a very good way for the privacy protection, I think it's something related to the social stuff, right? So for us, we really will like such a method very much, but for the government, probably they only want to, see use, but we are not allowed to use it, right? So, and this there will be some sort of conflict. So for example, now in China, maybe as long as this thing is going to be used by, and more people, there will have be some specific law, right? So say, okay, such a setup is only allowed to manipulate by the government company, so that if we want to have secure communication, we should also first handle our message to the government, then the government transfers to you. Then we have to believe the government. So I don't know, but some will already start to think about such a thing. Yeah.
Because the relationship between Paul and Cynthia, or Bob and Cynthia, in your model may be an asymmetrical relationship, right?
Right.
It was assumed to be a symmetrical relationship in your model, but that is not for granted.
But I think for the long run, if we really find some good quantum memory, then also we use the entanglement-based QTD. And for example, we can have some long-term and entangled relation or entangled state. Then, and after a while, and it's out of control of the government, because as long as we can make the quantum memory ourselves, then you can work around. Then when you need, then you can perform measurement on your particle. Then you can broadcast, say, okay, Jian-Wei, or I already sent you a secret message. Then this will be the ultimate, goal for the secure communication, I suppose.
Thank you very much.
Yeah.
Peter? Peter Netherland from Physics at Stellenbosch University. As I understand it, most of your experiments were done with the polarization states.
Right.
What's your opinion of using the spatial modes, entanglement in the spatial modes, and in a practical application? I know it works, but in a practical real-world life, so you can enhance your basis set, right? You can have denser information.
Right. Yeah. I think, and for the free space, if you use a many special mode, is not a very good way, because then the different special mode will go to the different modes, then you will have problem with the correction. So I think, but we could use time being stuff, right? So then we can enhance and key rate or something like that. Yeah. But in the fiber, probably the special mode is also not a good solution. Yeah. So I think maybe not. Yeah.
And Miklos Fellow here. We'd like to know if you have also plans about quantum computing.
Right. Yeah. And because, okay, so now people know a lot about what is going on and over the world. For example, so we have I think, two main things. So for many physicists work at the university, and for example, like myself, one of my main focus is about quantum simulation, because we believe in the short term, quantum simulation could really provide some useful solution for very difficult physical problems. So for example, we are working on, article system to study, to simulate the topic Fermi-Harmonic model for the mechanism of superconducting and so on. And we are very confident within the next 5 years we can provide something meaningful which cannot be computed by the super fast classic computer. So there are many people in the United States or in Europe or in China, we are working on quantum simulation. But there are also many companies, right? For example, like Google, IBM, and Intel, and also Microsoft include us because we are in collaboration with Alibaba. So we have joined the laboratory. We are working on superconducting, quantum computation, and so on. Then, maybe in the short term, we should be able to interpolate, for example, 50 particles or 100 particles to showing some advantage of quantum computation, but without taking care of any real application. We just want to talk some special and game to show for this game we are better, the quantum computer is better than the supercomputer. But to me, I think the quantum simulation is more important because which will really solve some practical problem. Yeah.
So, one last question.
You talked about teleportation.
Right.
So in this sense, teleportation is still just making a copy, so then there's two copies. So, right?
No, it's not a copy. So I clearly mentioned in my talk, so after teleportation, so the original state of the original particle has been totally destroyed. That's the precondition how quantum teleportation can work.
Okay.
So it's not a copy. Yeah. So that's very important. So you will be still unique, so different from the computer, right? People talk about we can download your sort, download your soul, and whatever. But a quantum mechanics is not possible, not even for a single particle. So we are quite safe. We are very unique in the university. Yeah.
So, Jian-Wei, I told you that shortly after the Shor's algorithm was published, I actually took some time to try and understand that, and I remember giving a seminar at the physics department at the time. Since then, I have only peripherally followed what has been developing, and I must say some of the initial skepticism that one encountered in the field of quantum communication and quantum computing in general seems to have made way for a wave of optimism, as illustrated by the remarkable technological advances that you were telling us this evening. So it was revealing. You had a tough task to speak to a general audience and communicate all of what you actually did. I think you were remarkably successful, and thank you very much for that. Thank you. Fortunately, I don't need a quantum communication channel to extend a simple invitation to you. Namely, I hope you will still have a bit of time to spend with us, enjoying some refreshments and a glass of wine, and perhaps reflecting on what we have just heard. Thank you very much.
Thank you.